Okay, last lesson we looked at the sine and cosine of our circular functions, and today we're going to look at a tangent. So beginning again with looking at the unit circle on a set of axes, so we can see that here. We're going to look at a tangent. So the tangent is this blue line. Remember, a tangent goes down and it touches just the edge at once. So we could label those points. So I'm going to label label the point where that tangent touches. I'm going to call that A. Now I'm also going to have this point here, and I'm going to call that P. And then up here, I'll call this point C, and down here at the origin, I'll just call it O. Now we have our angle in here as well, so we're going to look at that. So if you remember yesterday, we did the sine and cosine, and remember cosine is along the x-axis, so if we're looking along here, and the y value is the sine value where we look along the y. Now also remember that the radius of our circle is 1. Okay, so I've just drawn down here underneath the unit circle, I've drawn out these triangles that hopefully you can see. So the first one is where we go from the origin, and sorry, I might call this point here D, so you can see what I'm talking about, and that's D and up to P. Alright, so we can see that this green line is the radius, so that is 1. And knowing from yesterday, we know that the x value along there, so we can see along up to D, is known as the cos of the angle, cosine of the angle. And we know that the y distance up to this point P is the sine of that distance. So here's that little angle. So that's my first triangle. Now if I look at the big triangle created by the tangent, now, so really what we can see, this triangle is made from the origin going all the way out to A and then up to C. So we can see that from the origin to A is the radius, so that is 1. And what you also can see, if we can see, that we have the same angle here. So when we see that, and we have one side that is similar and an angle that's similar, and also they're both actually two angles that are similar because they're both right angle triangles. So because of that, we can say that the triangles OPD and the triangle OCA are similar. So when the triangles are similar, that means that you can say that their sides will be of the same ratio, and you can work it out. Now, if you have a look, so what I'm going to say is that if you look, so that when we say that they're of the same ratio, so if I said sine theta divided by cos theta, so that first triangle, that would create a ratio or of a number. So if we're saying it's similar, we're saying, and I'm going to call this side tan angle, because that one would be, okay, so we can say that it's similar to this, which is, and we've got tan, if I do the same sides, over 1. Okay, so if you see that, this is just to prove. So therefore, if you have a look, if I rearranged this formula we just did here to make tan the subject, we can see that we would move the 1 over, and you'd have 1 times sine theta over cos theta, which is essentially itself. So we end up with the rule that we can say that if you're trying to find the tangent of the circular function, tan is equal to sine theta over cosine theta. And so that is the rule that you will need to learn. Okay, now this is also, therefore, and it is provided that cos theta doesn't equal 0, because remember we can't have a 0 on the bottom of a fraction. So if it does, if cos equals, we would say it's undefined, that tan is undefined. And so if you look at it, if we can't have cos equals 0, and remember that cos is the x value, and so if you have a look, when is x 0? So that's here. And if you go up, so at pi on 2, x is 0. And also down here, if we were down here on 3 pi on 2, x would be 0. So that means cos 0. So we could say that tan is undefined at, and you can say pi on 2 and also 3 pi on 2. And then if you kept going around the circle, you could say 5 pi on 2, etc. So you just keep going around at those points, the top and the bottom. That's when tan will be undefined.